Hello and welcome to section 2.2a. In this section we're going to talk about polynomials of higher functions, and remember, if you have any questions on any of this stuff, please bring it to class so that we can discuss it. So the first thing we're going to talk about is polynomial functions. And a polynomial function in general has a graph that has no sharp turns, and it also is continuous. So we need to talk about it as a continuous function and no sharp turns. So continuous means no jumps, no holes, no asymptotes, no gaps or of any sort. So no gaps. So continuous, and then there's also no sharp turns. No sharp turns in this graph. Okay, so basically a polynomial function could be something like this, not this. So this is polynomial. This is not. Over here would be like a sharp turn, like an absolute value function, or a gap of some sort, or a hole, or something like that. So anything that you can draw continuously is a polynomial function. So then, what is the general form of a polynomial function? Well, we usually use a to the n, x to the n, plus a to the n minus 1, plus x to the n minus 1. And basically what we're saying is that in this, and it will continue on all the way down, in a little bit more layman's terms, we would say something like 5x to the 8th plus 3x to the 7th minus 6x squared, and so on all the way down. And we can continue all the way down until we run out of x's, and it doesn't have to have 8, 7, 6, 5, 4, 3, 2, 1, but we kind of talk about it as that's a polynomial function. What is the degree of a polynomial function? The degree of the polynomial function is always the n value, the highest power. So highest power that we have. So for example, in my previous one, 8 would be the degree in the blue one. In the other one, n would be the degree. And then what are the leading coefficients? Well, that's the first number with the highest power. So the one that goes with the degree is my leading coefficient. So in my red example, well, let's go back to this one. In degree for blue was 8. In degree for red, it was n, just because that's the way I wrote it. And then in this one, the leading coefficient would be in the blue. We're just going to use LC. Leading coefficient is 5. That's my example there. In the red, the leading coefficient is a to the n. So whatever is in front of our highest degree would be our leading coefficient. So that's just basically basics what of a polynomial is, polynomial function is. So now we're just going to sketch these, and we're going to see if there's any patterns with the degrees of the graphs. And some of these you've seen before. So for example, we have x squared. And so x squared you've seen as a parent function that we use quite a bit. So it looks something like that. And so you can see that it looks something like this. And so then we go to x cubed, which would look a little bit more like that. And so as you can kind of see, maybe we'll see some patterns as we go down the page. Well, x to the 4th, when graphed, will look more like this. And so what we're trying to see when we're looking at these is what is the end behavior of the graph as I sketch it? What's going on with the degree, with the power, and how the graphs are looking? So a 5th might look something like this. That's a cube. I gotta do something like that. There's a 5th. And also look at the max and minimums and things like that. So a 6 would probably be, and we don't usually sketch these guys, but there's a 6 and a 7, and so 7 would go something to that effect. And so let's talk about the degrees. We talked about the degrees And how they graph, well, if you look at the degree, a degree of 2, how many maximum minimums do we have? What is the end behavior? Well, and with a degree 4, what are how many maximum and minimums? And so if we're talking, you know, if you kind of look at this, well, let's just talk about x squared. All right. So if you look, x squared, the end behavior is both going up. X to the 4th, they're both going the same direction. X to the 6th, even though I used a negative, they're going the same direction. What do we notice about the odd ones? Well, in the odd ones, odd powers, they're going opposite directions. And it doesn't matter whether we're negative or positive, their odd ones are going the opposite direction, and if it's reflected. So then, that might be something we might notice with the degree. We also might notice that if you look at the number of maximum and minimums, there's, you know, if you look, I have a degree of 2, I have 1 maximum or minimum. In degree 4, I have 3 maximum or minimums. In 5, we have 1, 2, 3, 4 maximum minimum. I mean, there's a lot of things to notice when we're graphing these, but what we're basically trying to figure out with this is, you know, what is the end behavior? And that's the overall scheme of this. Is we're going to talk more about end behavior in just a second. So in the next one, this is what we're talking about with our end behavior. If we have our power, now this is talking about on our highest degree. So in our highest degree, if our n is odd, so this is saying like x cubed, all right, or x cubed, x to the 5th, x to the 7th, x to the 9th, and so on. You know, whatever the highest degree is, that's this n value. We have different n behaviors. And it all depends on what the leading coefficient is. When the leading coefficient is greater than 0, we will start at negative and we will end at positive. And this is the way they always are. So let's look back at the previous one. So if we look at the previous one, here's a leading coefficient of 1, here's a leading coefficient of 1. We started at negative and went to positive. And if we look at the next example over here, well, this is still following our odd pattern. You'll notice that when we have a leading coefficient that is less than 0, we start at positive and end at negative as we work our way across. So let's look back. Do we have any examples of those? Well, yeah, down here we had an example of we had a leading coefficient of -1, started at our end behavior was going positive, and it ended at negative. So that's really what we're talking about as we work our way across the page. And you can see we're talking about as x goes to infinity, we're ending up that our y value is going negative. When x was going to negative infinity, when we're going this way, we end up into the positives. And that's really what this is all saying here. So when x is going to infinity, we're going to positive. When x is going to negative infinity, we go to negative. So if the leading coefficient is positive in this case, then we can say our x values and our y values follow each other. When it is negative, when our leading coefficient is negative, they're reversed. So when x is going negative, y is going positive, and x is going positive, y is going negative. So something to kind of think about as you're looking at these. So then when n is even, so we're talking like x squared, x to the 4th, x to the 6th, oops, and so on, then we end up with this happening, that if our leading coefficient is greater than 0, then our end behavior as x goes to negative infinity, we're going to positive, and as x goes to infinity, we go positive. So basically what we're saying is when we're counting out this way in our x's, our y value is going to infinity, and when we're counting out that way in x's, our y value goes to infinity also. So let's look back and see if we have any examples of that. Well, look, our x squared, x to the 4th, do that. As we're going out in our x values, as our domain gets bigger or smaller, our y values get bigger. And then in the previous example, when we talked about if we have our leading coefficient being negative, then as x goes to negative infinity, as we go this way and our x's count out in our x's, our y values go down. And same thing as we count out in positive infinity. So when we have an even function, when we have our even function, it basically that's either going to both open up or both open down depending on what our leading coefficient is, whether it's positive or negative. If it's positive, it's opening up. If it's negative, it's opening down. And so if we go back, we can see that as our example when we had x to the 6th down here. When we had x to the 6th, we had one that both went down because of our leading coefficient was -1. So that's kind of our leading coefficient test. So we kind of look at it as a way to figure out what's happening with the graphs without having to actually go ahead and graph them. So then it says, using the leading coefficient test, describe the left hand and right hand behavior of the following. Alright, so I'm looking at this and I see a degree of 3. So we know this is odd. So first thing I know is we're going to have one up and one down. Now I don't know which order they're in yet because I haven't looked at the leading coefficient. So when I look at the leading coefficient and I see that the leading coefficient is negative, so we have a negative leading coefficient, that means as x goes to -infinity, my y value will have to go, my y value, my f of x, or g of x in this case, will have to go to positive infinity. They're opposite each other. So actually I did this right. And as x goes to infinity, as it goes out to the positive side, f of x will go to, my y value will go to -infinity. So they're opposites of each other in this case. So then I'm going to look at my next one here, and I see, oh, okay, now this is even, my degree is even. So now I'm thinking both up or both down. They could both go up or they could both go down, just depending on the leading coefficient. I haven't looked at the leading coefficient yet. And so now if I look at my leading coefficient, I see that there's a 1 there, so this is positive. So that means that as x goes to infinity, my y, my g of x in this case, will go to positive infinity. They go the same direction. As x goes to negative infinity, then g of x will also go to infinity. All right, so when they're positive, when the leading coefficient is bigger than 0, then I'm going to go they're both going to go to positive. So then I look down here that my g of x, so I look first of all at the degree. I see the degree is odd again. And in this case, since it's odd, that means that I'm going to have one going up and one going down. And then I look at my leading coefficient, and my leading coefficient is negative again. So this is a lot like the previous example, that it doesn't matter that I have different degrees in this case. It just means that as x goes to negative infinity, my g of x in this case is going to go to positive infinity. And I would say if I was probably rewriting this one, I probably would have said make that a positive so we could talk about the opposite thing happening. And so then it would have been as x goes to negative infinity, y would be going to negative, and then vice versa. So we're basically talking about this, and this is, we can write these, and this is the way we'd write them as if we were in calculus. So just moving along then, hopefully you kind of understand what's going on here. And then, so then we can talk about the zeros. And so with this is just information about different names. So when we take a polynomial and we factor it or do long division or complete the square or whatever we do to find out where the graph is crossing the x-axis, when we find what x is equal to, we call that a zero. We also call it a solution. Another name for it is a root. There are many names for the same thing. Also, this is the same place where the x-intercept pops up. And so as we do this, there are, you got to understand that we're going to ask you in many different ways for the same thing. And so they may say, find the root of this, find the zero, find the solution, find the x-intercept. All of these guys, all three of these, 1, 2, and 4, are basically asking you to find out when f of x, when your y value is equal to 0, what is my x value? And that's basically setting the polynomial equal to 0 and finding out where it's crossing the x-axis. And so all of those are doing the same thing. So you just kind of got to get used to it, that we're going to ask you multiple ways for the same thing. And this doesn't go away. This is something that we do in calculus. We ask for certain things in calculus different ways, but we're asking the same thing over and over again. The only one that's really different is this factor, the polynomial as a factor, and basically these are x minus a is what we solved. We would say x minus a, so, we'd get something like x minus a times x minus b, so on and so forth to get a polynomial, and basically these guys are what we set equal to 0 to find the solutions, the roots, the zeros, the x-intercepts. And so then we would solve a factor, x minus a equals 0 or x minus b equals 0, and we find out those are the places that it's crossing the x-axis. So when we ask you for all of these different ways, it's basically asking you for the same thing. All right, so in example 3 here, it says find all the real zeros of f of x algebraically and then graphically. All right, so first thing, I'm going to do it algebraically. And so we have f of x equals x cubed minus x squared minus 2x. And to do it algebraically, I have to do some factoring. Or, well, yeah, I have to factor. That's pretty much my only option. If this was a quadratic, meaning that the this thing was squared instead of cubed, I could then use the quadratic formula to do it, and that would be the only other way to do it algebraically. But since this is a cubic function, first of all, let's just kind of talk about it, remind ourselves what we were talking about with opening up, opening down, things like that. So let's talk about it. So this degree is 3. So with a degree of 3, what does that mean for our end behavior? Well, that means that it's either that it's going up and going down, or vice versa. We look at do a leading coefficient test real quick, and a leading coefficient test is positive. So when we look at that, our leading coefficient is positive. So that means it's actually going the other way. That as x goes to negative infinity, as x gets smaller and smaller, as we're counting out in the x, our y value, our f of x in this case, will go to negative infinity also. So they follow each other when they're the same. And when x goes to positive infinity, that means that our y values go to positive infinity. And this is just kind of just remembering what we did a few minutes ago. Not that they weren't even asking me that, but that's also kind of helpful because it might help me determine whether I'm going to get a maximum first or a minimum first, or when we look at our graphing calculator. So we're going to kind of work with a sketch to do this. So when I do this, so I'm going to go ahead and factor this. So f of x is, well, you'll notice that all three terms have an x in common, so I'm going to remove the x from the problem, and then I get this nice little quadratic that I could use my box method or whatever, however you want to solve this, to factor it. So I'm going to say, okay, well, let's see. I have negative 2 when I multiply the factors together, and it looks like I need negative 1 when I add them together. So if I do that, that would mean my only choices are really 2 and 1. But if I'm going to add them together, I need to get negative 1. So that would mean that my 2 has to be negative. And so negative 2 times 1 would get me negative 2, and negative 2 plus 1 gives me negative 1. So now I can just go ahead and factor this inside part. And it says x times x minus 2 times x plus 1. So now I've factored it completely. And so if I want to find the zeros, that means that when I am asking to find the zeros, I set f of x equal to 0. And that means replace this f of x value with 0. And so 0 will equal these factors. And so these factors right here are basically what we were talking about up above. There are factors, and when we have factors, we set our factors equal to 0 using our zero product property, which means that if I make x equal to 0, that would be, if I solved that, that would be one solution. If I set x minus 2 equal to 0, that'll be another place it crosses the x-axis. And if I say x plus 1 equals to 0, that would be a root for this, or a 0, or a solution, or even an x-intercept. All of these guys are going to be the same thing. And so because I've set my y equal to 0, then the x value that I found will be an x-intercept, a solution, or a 0. Just different ways of saying the same thing. So you'll notice that my solutions for this one is that x is 0, x is positive 2, and x is negative 1. So knowing this, all right, so I'm going to sketch a quick graph. So knowing all of these things about it, knowing my end behavior, and knowing these zeros where it's crossing the x-axis, I can get a pretty good idea of what my graph is doing without actually having to graph it. And this is kind of key because sometimes you don't have a calculator, sometimes you don't have access to these things. So you're going to have to kind of get a general idea of what these graphs are about, and the more you do this, the better off you are. So I know that I'm crossing at x equals 0, so I got a point there. I'm also crossing at -1, which would be like right there, and I'm crossing at +2. So we're looking at a point there. So with my end behavior, as x goes to -infinity, the graph is falling. As x goes to +infinity, the graph is increasing. So then if I wanted to find what the graph is doing, I know it's got to cross here. It's probably going to do something like this, and since it's a cubic function, it's got to have one peak and one valley. It's got to go above and below the graph, so it's probably going to look something like that. Now I don't know, I haven't graphed it yet, so let's get out my graphing calculator and graph this thing. There it goes. Rid of all the other stuff that's in here. And I guess, well, I'll just clear all these out real quick. And so then the function that I want to graph is x cubed minus x squared. And when I graph this thing, if I go to my standard window to start with, and there you go. That looks pretty close to the sketch that I had there. And so, I was supposed to find the local maximum minimums. I'll go back to that in just a second. But you can see that my graph that I have here is pretty close to what I was doing, and I did that with just the end behaviors. I know I'm a little off because of this thing over there, but this is just using the end behaviors and the local maximum minimums to help me find that. So, or the end behavior and then my zeros to find that. So now to find my local maximum minimums, now we're just going to go through and go second calculate at second trace, which is calculate, and I'm going to find, it looks like a maximum first because it goes up first, and so I'm going to go down and do a maximum. And so if I go past it, go below it, and then go above my maximum, I messed it up, sorry. I'm going to clear that. Alright, let's try it again. Last try. Alright, so maximum is 4, and so I want to go to the left of the maximum, I want to go to the right of the maximum, and I want to hit the maximum. And so it looks like my maximum value, and I'll just pull it out of here, is that. Alright, and you can go to 2 decimal places. And so then if I want to go to a minimum, I'm going to go to my minimum and go to the right of my minimum, to the left of my minimum. And I think I said those backwards, but you get the point. And so there's my minimum, and so now I have my maximum and minimum on from my calculator. And basically we could write them as ordered pairs if we would like. And so our maximum in this case, we would write as -0.55, comma 0.63. So there's our maximum from our calculator, and our minimum then would be 1.22 and -2.11. And so that's what we're looking for when we do it with our calculator. They do exist, and therefore those are the points for them. So thank you for watching today's lesson on 2.2a. If you have any questions, remember, on any of these examples, please bring them to class. We can cover them in class, and I look forward to seeing you in class.